So here we have the um, the different serving sizes and calories contained within various different fast food items. And here we have the random element, which is a method for sampling randomly. And so we have a sample size of 30, and then here is the serving size, and here's the calories. Um, Here is a summary sheet with a histogram and various different data points. If you look at the histogram, you can tell that it's skewed to the right. And it's the data set is multimodal. For me, it seems like the mean would be the most relevant measure of center, just because if you were to look at the median, it would, the mean would be like a better measure. So yeah, I think the mean would be the best measure, but the measurement that's closest to the mean is the median. If using the empirical rule, if you look for the percentage of the data that's beyond 2 standard deviations of the mean, you get 5% of the data. And if you compare that to the Chebyshev rule from chapter 3, you'll find that that 25% of the data is beyond 2 standard deviations of the mean. So there's kind of a large difference between those two values. So here we have a confidence interval, which means we're going to use our sample data to estimate a parameter about the population. So the variation in the sample will be an indicator of the variation in the population. Here we can see that n equals 30, and our sample mean is 482-ish. Standard deviation and our t-value. So there's our formula for the confidence interval. So you're going to take the mean, and you're going to find the lower interval. You're going to add t times standard deviation over the sample size squared. And to find the upper interval, you're going to add instead of subtract there. And you can see the work below the formula here. And so once we've gotten, since we're using a 99% confidence interval, this can be interpreted as, we can be 99% sure that the mean number of calories per item at U.S. fast food restaurants is somewhere between our lower limit 360 and our upper limit, our lower interval and our upper interval 360 and 604. Here we have a hypothesis test, and we know it's about a proportion because the question discusses a percentage. we're going to use a significance level of 0.05. So to find the null and alternative hypothesis, first you want to state the claim. So the claim is that a majority, which is greater than 50% of fast food items, have a serving size more than 200 grams. And the opposite of that would be less than or equal to 50%. So since there's the equal sign in the opposite, that's going to be our null. And then our alternative will be the claim. Then we have to find our test statistic. And we plug in those numbers, and 0.5, which is our sample proportion, minus 0.5, which is our population proportion, is 0. So 0 out of anything is 0. So our test statistic is 0. So when we have a significance level of 0.05, the critical value is 1.645, and that, if you look at the picture, it separates the rejection region from the fail to reject region. We can clearly see when you compare 0 to 1.645 that the test statistic 0 falls in the fail to reject region. That means we fail to reject the null hypothesis, and we know nothing. For the p-value method, we have two possible decisions. Reject the null if the p-value is less than or equal to alpha. Fail to reject null if p-value is greater than alpha. Alpha is 0.05. H1 is greater than 0.5. You get a test statistic of 0. So you find the area to the right of your z-score 0, and that's 0.5. And you find that p-value 0.5 is greater than alpha 0.05, so we fail to reject the null hypothesis. Here we have a chart that shows the linear correlation between serving size and calories in fast food items. Serving size is on the x-axis and calories is on the y-axis. That just makes the most sense to me, but I believe that you could switch those axes and it would still make sense. We have a line of best fit going through the data points, and at the top we have an equation representing the line of best fit. There's a clear correlation because the coefficient of determination, r squared, is on a scale from 0 to 1. It's on the higher end of that scale. So there's a significant correlation between serving size and calories. And this can be used to make predictions. The line of best fit can be used to make predictions about how many calories based on how many grams the serving size is, and vice versa. I would tend to believe a prediction in the lower left more than I would in the upper right of the line, just because we have data values that are close to that estimation. So I'd say the limits of the prediction, it's less accurate the higher the serving size gets. So I'd say if you're trying to make a prediction, you wouldn't want to go past around a 400 gram serving size. It becomes less tightly correlated